A queue can be viewed as a list where items are inserted from one end and removed from the other end. To access element in the queue, we have to follow the rule first in, first out. It means that the first element inserted in the list will be the first element removed from the list. For example, if we insert 5, then 3, then 2, then 8, so the first element inserted, only the first element inserted can be removed. If we remove the 5, we can then remove the 3, and then the 2, and then 8. And the queue has two ends. The first end is called, where we insert, is called the rear. The other end is called the front. So the queue has two operations: enqueue, which insert an element at the rear, and dequeue, that remove an element from the front. We can implement a queue using a linked list. So enqueue will be add at the end, and dequeue will be remove front. So to add the end in enqueue, this operation will take big O(n), and to remove from the front, it's take big O(1). So this solution is not very good. There are another implementation using a doubly linked list. So a doubly linked list is better. Why? Because there is two pointers, a pointer to the front and another pointer to the end of the list. So the enqueue operation, when we add at the end, will take only O(1) in enqueue, because we have another pointer at the end, and we have big O(1) in the queue. We can also implement a queue using an array. This implementation requires a size. We have to give a size to define the array in which we will insert items. So we may insert items at the end of the array and remove from the front. For example, we can insert 5, then 3, then 10, and 6. We have this is the front, and this is the rear of the queue. So if we dequeue from this queue, so we will move the front forward, and for the front will be equal to front by +1. In that case, the front will be at index 1. Then if we dequeue also another time, so the front will be equal to the index 2, and so on. Now if we enqueue, we may add some values like 8, 9, and 11. At this stage, we have the rear here. As you can see, the queue is not full. Why? Because we have some element here. We have to use this empty spaces. So there are two solutions. The first solution is to make shifting every time we make a dequeue. So when we dequeue an element, we have to shift all the element in the queue and remove these spaces. And the solution require big O n time. The second solution is to use a circular array. So when the rear reach the end of the array, in a circular array, the rear will be, when we make an enqueue, for example of 12, the new value will be at index 0, and the rear will come back to the beginning of the array. The same thing for the front. If we make many dequeues, the front, when it reach the end of the array, it come back to the first index of the array. We can implement the circular array by using the modulo operator. As you know, when we enqueue a value, the rear will be incremented by 1. So the rear will be equal to rear plus 1. And when we dequeue, the front will be incremented by 1 also. But in that case, the rear can be reached the end of the array and go to an index that is out of bounds of this array. So to handle this problem, just we will make the rear will be equal to rear plus 1 modulo the size of the array. The same thing, the front will be modulo of the size. When we have a value modulo size, x modulo size, x modulo size will be between 0 and the size minus 1. For example, if we have 5 modulo 10, we will get 5. 12 modulo 10, it will be equal to 2. 10 modulo 10, it will be equal to 0. The same thing here. The rear will be between 0 and the size minus 1, and also the front will be always between 0 and the size minus 1. Let's take an example. Suppose we have this array index 0, 1, 2, 3, 4, 5, and 6. So the size of the array here is equal to 7. And we will suppose that we have the front here and the rear here. I have the value 5, 2, 8, and 3. Okay. So the front, in that case, the front is equal to 3. And the rear is equal to 6. So if we enqueue a new value in the list or in the queue, if we enqueue 12, so rear will be equal to rear plus 1, which is equal to 6 plus 1 modulo 7, which is 7 modulo 7, which is equal to 0. So the rear will be moved to index 0, and we can put here the value 12. The same thing for the front. If we dequeue, we make 4 dequeues or 5 dequeues, the front will be at index 0. If we make 2 other enqueues, for example enqueue 7 and enqueue 9, so we will get 7 here and 9 here, and the rear will be here. At this stage we have the rear is equal to the front minus 1, or rear plus 1 will be equal to the front, and we can see that the queue is full. So if the rear plus 1, we work always modulo the size is equal to the front, it means that the queue is full. So let's make some dequeues. So if we dequeue the 5, we make a dequeue. The front will be at index 4, dequeue, 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 dequeue. At this stage we have the front equal to the rear, we have only one element, and we make another dequeue, we will have the front also after the rear. So the same thing, the rear plus 1 modulo the size is equal to the front. So how do we know if the queue is empty or full? So there are many solutions. One solution is to make a counter that count the number of elements in the queue, and if the counter reach the size of the array, so we know that the queue is full, and if the counter is equal to 0, so the queue is empty. Or we can use an extra element. So if we have the size 7, we make an extra element in the array, and the array will be to index 7, and we make some rules. If the rear plus 1 modulo size is equal to the front, that means that the queue is empty. If the rear plus 2 modulo the size equal to the front, this means that the queue is full. Let's take an example. If the user define a queue of size 7, we will define internally an array of size 8. Suppose that the front began from the index 4 and the rear at index 0. So if we enqueue 12, the rear will be at index 1. If we enqueue also the value 7, the rear will be at index 2. Now, if we try to enqueue another value, we cannot use this extra space in enqueuing. So before enqueuing, we have to check if the rear plus 2 is equal to the front, then the queue is full. And if we dequeue now, so if you dequeue, the front will be at index 5, then at index 6, dequeue at index 7, the front here, here. If we have the front is equal to the rear, that means what? That means that there are only one element in the queue. And if we make another dequeue, the front will be equal to the rear plus 1. In that case, as you can see, we will get an empty queue. Let's move now to the implementation and trying to implementing all these rules. The first thing to do is to create a queue class. We have 4 attributes. The first one is the size of the queue, which is integer. We have the front, the rear, and an array queue. The constructor will be a constructor with one parameter, which is the size. So if we create a queue, we have to give a size. And as I mentioned, I said earlier, when the user gives a size, we have to make an array with size plus 1. So this dot size will be equal to the size given by the user plus 1. And then make queue will be equal to the new int of size, or this dot size. This dot size. The queue will be empty, so we may choose any value for the front, any value between 0 and the size. We can take the value, for example, 0 by default, and the rear have to be equal to the front minus 1. So the rear will be equal to the front minus 1. To check if the list is empty or not, we make a Boolean method, empty, that returns rear plus 1 modulo the size equal to the front. So if the rear plus 1 modulo size is equal to the front, then the queue is empty. To check if the queue is full or not, just we return the rear plus 2 modulo size is equal to the front. To get the value in the front, int get front, we have to check if not empty, return queue of front, else return, for example, minus 1. To dequeue an element from the list, void dequeue, we have to check if the list is not empty. So if not empty, just we will increment the front by 1. So front will be equal to front plus 1 modulo the size. To enqueue an element, x in the queue, we have to check if the list is not full. So if not full, in that case the rear will be incremented by 1 plus 1, of course, modulo size, always modulo size, and then queue of rear will be equal to the x we move to the testing part. So we will create a new queue equal to new queue with size, let's say 5, and we will make a loop for we'll make I less than 10 to see if there is any error. So queue dot enqueue the value I. And then to print all the elements in this queue, we will make a loop while not queue dot empty sys out queue dot get front plus a little space and then queue dot dequeue. Let's run. We will have 0, 1, 2, 3, 4, and that's it.